Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so I'm very happy to introduce Ewan Gwynn, a brilliant young probabilist from MIT working with Scott Sheffield, who has been an intern here this summer with David and me, and he will tell you about our joint project on first passage percolation.
All right, thanks. So today I'm going to be talking about a variant of the Eden model, equivalently first passage percolation, where edges are weighted by a positively homogeneous function. And this is also called the Polya aggregate model. And this is based on a joint work with Sebastian Bubeck. So I'm going to start by introducing the unweighted Eden model and the first passage percolation model. And then I'm going to talk about the particular model that I'll consider in this talk. So the Eden model is a random growth model on ZD. It's important in a variety of fields because it can be used to describe things like the growth of bacterial colonies, lichens, mineral deposits, the diffusion of information through a network, and so forth. So to define this model, we start by sampling an edge uniformly at random from the set of all edges of ZD, which are incident to the origin. And we let A1 tilde just be the singleton set, which consists of this one edge. So just start with one edge. Then inductively, if for some positive integer n, the set an minus 1 tilde has been defined, we sample an edge en uniformly from the set of all edges which are incident to the boundary of an minus 1 tilde, but which are not actually contained in an minus 1 tilde. And we let an tilde be the union of an minus 1 tilde and the singleton set en. So maybe this is what it looks like after 2 stages, and then after n stages, we get a big cluster of edges, and then we add one more at each stage. So first passage percolation is another random growth model, which can in some sense be viewed as a continuous time reparameterization of the Eden model. So this model is a little bit more complicated to describe, but it also is more tractable mathematically. So to define this model, we start with a collection x sub e for each e in ZD of IID exponential, for each edge e of ZD of IID exponential random variables. And for a path eta in the integer lattice, by which we mean a connected sequence of edges in the integer lattice, we let the passage time of eta, which we call t of eta, be the sum of xe over all of the edges e in the path eta. And for a vertex v of the integer lattice, we define t of 0v, the passage time from 0 to v, to be the minimum of t of eta over all paths eta which connect 0 to v. And then we define a growing family of subgraphs of the integer lattice, which we call AT, as follows. For each t, we let the vertex set of AT be the set of all vertices v in ZD, whose passage time from 0 is less than or equal to t. And we let the edge set of AT be the set of all edges in ZD, which lie on paths started from 0, whose passage time is less than or equal to t. So this gives us a growing family of subgraphs of the integer lattice parameterized by the positive real numbers. And it turns out that first passage percolation is equivalent to the Eden model in the following sense. So suppose that for each positive integer n, we let t sub n be the smallest t for which AT has at least n edges. Then this gives us another growing family of edge sets parameterized by the positive integers, and it has exactly the same law as the Eden model clusters. And this is just an easy consequence of the memoryless property of the exponential distribution. So one of the most fundamental theorems about, yes?
Question on the previous slide. So the set that you define, in the Eden model, the set of edges that you use always form a tree, yes?
No, they don't form a
They
tree.
can form cycles.
Right, because you're just selecting uniformly from the set of all edges that are adjacent to the current cluster that you haven't selected yet. So, like in this picture, maybe here instead of selecting this red edge, we could select this edge here, and then we would form a cycle.
Okay, so it's not the edge that connects to the outside.
No, it just has to be some edge, which has not been hit yet. Okay, so one of the most basic theorems about first passage percolation is this following result, which was originally proven by Richardson, and various strengthenings and generalizations were proven by Cox and Durrett and Keston. And it says that there is a deterministic, compact, convex set bold A, which is symmetric about the origin, such that the first passage percolation clusters converge to AT in the following sense. For each t, it holds except on an event of probability decaying faster than any power of t, which is what I mean by this notation, O sub t infinity of t here, that the vertex set of AT is approximately equal to t times bold A intersected with ZD, modulo these polynomial order errors. So although we can get very strong convergence statements about the convergence of the FPP clusters toward bold A, we know almost nothing about the set bold A itself beyond the fact that it's compact, convex, and symmetric about 0. It's not even known, for example, whether or not it's a Euclidean ball except in dimension greater than or equal to 35. So this is a very poorly understood object. But it's not hard to simulate the set bold A by just running a simulation of the Eden model. And so here's such a simulation, which was generated by Sebastian using MATLAB. And as you can see, the limit shape appears to look like a Euclidean ball, but maybe it's off by a little bit. So it's approximately a Euclidean ball, but it's conjecture that it's not exactly a Euclidean ball. So in this talk, I'm going to be interested in the following natural variant of the Eden model, which can be described as follows. Suppose we have a weight function, which we call WT, on the set of all edges of ZD. So each edge is associated a weight, WT of E. And suppose that we do the standard construction of the Eden model, except that at each stage, instead of selecting the next edge En uniformly, we select that edge with probability proportional to the weight of E from all of the edges which are incident to the previous cluster. So, as is the case for the ordinary Eden model, this weighted variant of the Eden model is equivalent to a weighted variant of first passage percolation, where we have independent exponential random variables at each edge, but instead of all having parameter 1, the parameter of each exponential random variable is given by the weight of the corresponding edge. And again, this is just a consequence of the memoryless property of the exponential distribution. So in this talk, I'm going to focus on the weighted Eden model, where the edge weights are given by an alpha positively homogeneous function for some real number alpha. So there's a number of reasons for considering this particular variant of the weighted Eden model. First is that it's a natural generalization of the standard Eden model, both because of just intrinsic mathematical interest and because in the situations that the Eden model can be used to model, remember like the growth of mineral deposits and the spread of information and so forth, it's natural to consider what happens if you allow the growth rate to depend both on the distance to the origin and the direction in which you're growing. Additionally, it turns out that diffusion limited aggregation, or DLA, which is another important random growth model, is actually equivalent to a weighted variant of the Eden model on a d-ary tree, where instead of having edges which decay polynomially as we move away from the origin, or instead of having weights which depend polynomially on the distance to the origin, we have weights which depend exponentially on the distance to the root. And this model was studied by Aldwis and Shields and by Barlow, Pimentel, and Perkins. And finally, recently in the computer science literature, a variant of the weighted Eden model with positively homogeneous edge weights, which is the particular model that we're considering in this talk, was proposed as a protocol for spreading a message while obscuring its source. So these are some reasons to be interested in the model considered in this talk. So now to formally describe the situation that I'm going to consider for the rest of the talk, we fix some real number alpha, and we fix a function f0 from the Euclidean unit sphere to the positive real numbers, which is Lipschitz continuous. And we let f be the function which is given by the Euclidean norm of z to the alpha power times f0 of z over absolute value z. So that f is locally Lipschitz and positively homogeneous of degree alpha. For example, we could have that f of z is equal to the alphth power of some norm on Rd.
You say positively homogeneous, are you saying because alpha appears without a minus sign? Because alpha need not be positive, right?
No, by positively homogeneous, I mean that f of constant times z is equal to the absolute value of the constant to the alpha times f of z. A function which is just homogeneous would mean that if you took like f of negative z, it would be equal to negative f of z. But that's not the case here.
Yeah, that wouldn't work for any power then.
Right. Right, so we consider positively homogeneous rather than signed homogeneous.
I see.
Okay. So yeah, but alpha can be positive or negative. And so in this talk, we're going to consider the weighted FPP model, where the weight of each edge E is given by the value of f at the midpoint of that edge. And we call this model F-weighted FPP. And note that in the case when f is identically equal to 1, so that alpha is equal to 0, we just get the standard FPP model. And in the case where d is equal to 1, so we're just working on the line, and f of z is equal to 1 over z, we get the Polya-Ern model. So in some sense, our model can be viewed as kind of a vast generalization of the Polya-Ern model, and this is the source of the name Polya aggregate. So,
this typo, it should be plus 1.
yes, sorry. It should be plus 1 here. Okay. So now that we've introduced the model, I can state the main results of my project with Sebastian. So first, in the case when alpha is less than 1, for any choice of the function f, we get a deterministic limit shape in the same sense as for unweighted FPP. So we have some simulations in this case. So if we take alpha to be equal to -2 and f of z to be the L1 norm to the -2 power, then our limit shape kind of looks like a slight rounding of the L1 unit ball. And if we take alpha equal to 0 and f of z to be the ratio of the L1 norm to the Euclidean norm to the third power, so this means that the restriction of f to the Euclidean unit sphere, which we called f0, is going to be big on the diagonal directions, but smaller on the horizontal and vertical directions. Then we get this kind of four-leaf clover shape. All right, so that's what happens in the case when alpha is less than 1. In the case when alpha is greater than or equal to 1, things are a bit more complicated, and we need to introduce a new notation to describe our results in this case. So if alpha is strictly greater than 1, there almost surely exists a finite t for which at is infinite. This should be strictly greater, not greater than or equal to. And we call tau infinity the smallest such t. So tau infinity is in some sense the time that it takes for the FPP clusters to get to infinity. And this is kind of easy to verify and will be an easy consequence of some of the estimates, which I'll describe later in the talk.
Probably just along a line.
Sorry, what?
Just reach infinity in finite time along a straight line.
Yes. Right. So it's an easy estimate to prove. So our first main result in the case when alpha is bigger than 1 is the following. So for each alpha bigger than 1, there exists some norm nu, which may depend on alpha on Rd, such that if we take our weight function to be given by the alphth power of nu, then almost surely all but finitely many vertices of the time infinity cluster a tau infinity are contained in some Euclidean cone of opening angle less than pi. So here's a simulation in the regime where alpha is bigger than 1. So this is with alpha equal to 5 and f of z given by the Euclidean norm. And here, as you can see, we start here and we go off to infinity in one direction. So this is very different than the case when alpha is less than or equal to 1. Note though that this Euclidean norm is not the norm that we actually prove the result for. The purpose of this picture is just kind of to illustrate what happens in this case.
But you think it's true for the Euclidean norm?
Yes, we do think it's true for the Euclidean norm, but it's not the one that we can actually prove it for.
And lots of others as well, presumably?
Yes,
But there is
but not for all norms, as you'll see from our second theorem, which says that for any choice of the function f0, which remember is the restriction of f to the unit sphere, there is some small positive constant c, which depends on f0, such that for any alpha between 1 and 1 plus c, almost surely zd minus the vertex set of a tau infinity is finite. So all but finitely many vertices of zd are almost surely hit, and in particular, it's the cluster is not contained in a cone of opening angle less than pi. So in particular, this tells us that in theorem 2, we cannot take the same norm nu for every value of alpha. So for example, if we took the Euclidean norm, there would have to be an alpha slightly bigger than 1 for which the cone containment result is not true. So here we have a simulation in this regime where alpha is slightly bigger than 1. So as you can see, it doesn't appear to have a deterministic limit shape because it's growing at different rates in different directions. But on the other hand, it is growing at a positive rate in every direction, so it's not going to be contained in some cone. All right, so here's the summary of the results. And I just want to point out here that in each of the 3 results, the corresponding object is a deterministic functional of the function f and the standard limit FPP limit shape bold A. So even though we don't know bold A explicitly, if we did know what bold A looked like, we could give an explicit description of the limit shape in the case when alpha is less than 1, the norm nu in the case when alpha is bigger than 1, and the constant c for a given f0. So now that we've stated the main results, we can proceed to the proofs.
Just about the results again. If you stick to the Euclidean metric to the alpha, you do know that for large enough alpha, you have a cone?
No, we do not know that. This remains an open problem to show that, to answer whether it's true that if you fix a norm nu, then it's almost surely contained in a cone for large enough alpha.
Can you just flash the results again, the previous slide?
Okay. So everybody.
And so this finite complement really is going to be non-empty to everything, is it? Because you have some places where you just don't have
because it's always because it gets to infinity in finite time,
Yeah,
so it's always true that if you fix some vertex, then with positive probability, there's a path to that vertex with passage time which is less than the time to infinity. So you're never going to have. Things can always fluctuate by a finite amount. Okay, so now for the proofs of our results. So the main idea of our proofs is that we're going to approximate F-weighted FPP passage times by a certain deterministic metric, which depends on F and on the standard FPP limiting shape bold A. So to define this metric, we first define a norm mu, which is just the norm on RD whose closed unit ball is bold A. So mu of z is the smallest r for which z is contained in all r bold A. And this gives a norm because bold A is compact, convex, and symmetric about 0. Now, if we're given a piecewise linear path gamma from some interval 0t to rd, we say that gamma is parameterized by mu length if for each t in 0 big T, the mu length, the sum of the mu lengths of the linear segments that gamma has traced up to time t is just equal to t. Okay, so it travels t units of mu length in t units of time. And for such a path gamma, we define the d length of gamma to be the integral from 0 to t of 1 over f of gamma of t dt. Okay? And for points zw in rd minus 0, we define d of zw to be the infimum over all paths gamma from all piecewise linear paths gamma from z to w of the d length of gamma. So this D is a metric on RD minus 0, and it's a metric, it extends to a metric on all of RD if in fact alpha is less than 1. And it has the following scaling property. For any Z and W in RD and any R greater than 0, the distance from RZ to RW is equal to R to the 1 minus alpha times the distance from Z to W. This is just an easy consequence of this formula here. All right. So the reason why we're interested in this metric D is the following lemma, which is going to play a crucial role in the proofs of our main theorems. So what this says is that we're given any stopping time for the filtration generated by the FPP clusters and any positive integer m. Then except on an event of probability which decays faster than any power of m, it holds for each vertex in ZD, which is not in the time tau cluster, and has its Euclidean norm proportional to m. It holds that the passage time from 0 to v minus tau is approximately equal to the d distance from v to a tau in the following precise sense. So we get these exponents which tell us how close the approximation is, and then we have an error which is some negative power of m. So now suppose that we're given, I'm not going to give a fully detailed proof of that lemma because it's a bit technical, but I'm going to give a kind of a heuristic argument for why we should expect it to be true. So suppose we're given a vertex u in the time tau cluster a tau. And then we observe that near u, our clusters grow like standard unweighted FPP scaled by f of u and translated by u, right? And by the limit shape result for standard FPP, the limiting shape of this process is going to be the ball of radius f of u centered at u in the norm mu, which is just f of u bold A plus u. So for each small epsilon greater than 0, it holds with high probability that a tau plus epsilon minus a tau is approximately equal to the union over all vertices u and a tau of the mu ball of radius epsilon f of u centered at u intersected with zd, right? Because we just apply this observation and then we take the union over polynomially many vertices. And because this holds, because the limit shape result holds except on an event of probability decaying faster than any power of m, and we only have polynomially many vertices with distance to the origin proportional to m, we get that this approximation holds with high probability. Now, if we're given a positive number t, we choose some small epsilon, and we break up the interval from tau to tau plus t into increments of size epsilon. And then we use the definition of the metric mu, and we find that, in fact, a tau plus t minus a tau is approximately equal to the d ball of radius t around the vertex set of a tau intersected with zd, right? Because we're just kind of averaging the function f over increments of which size depending on mu. And so if we're given any vertex, as in the statement of the lemma, we find that the time it takes to get from a tau to v is approximately the d distance from v to a tau. And that's why this lemma should be true. So this kind of illustrates what's happening here. If we start with a set a tau, which is this set in blue, then it's going to grow kind of like the FPP process after time tau is going to grow kind of like the d balls centered at a tau. So it's going to grow. So if alpha is bigger than 1, which is the regime that's shown in this picture, then it's going to grow faster when we're further away from the origin, and it's going to grow slower when we're closer to the origin. Okay. Right. So now that we've got our main lemma, we can move on to the proofs of the main theorems. So first, we're going to consider the case where alpha is less than 1, which, as you may recall, is we're claiming that there's a deterministic limit shape of the FPP clusters in this case. So when alpha is less than 1, each point of RD lies at finite distance from the origin in the metric D. So we can extend D to a metric on all of RD. So in particular, the ball of radius 1 centered at 0 in the metric D, which we call bold B, is well defined. And by scaling, we note that bold B is just equal to r to the negative 1 over 1 minus alpha times the D ball of radius r centered at 0. And it turns out that, in fact, bold B is the limiting shape of F-weighted FPP in the following sense. So we take these exponents chi and chi tilde, which will give us our rates of convergence. Then for any t, it holds except in an event of probability decaying faster than any power of t, that the vertex set of AT is approximately equal to t to the 1 over 1 minus alpha bold B intersected with ZD. So this is essentially the same as the limit shape result in the case of unweighted FPP, but just with somewhat different exponents. All right. So to prove this theorem, we proceed as follows.
Do you think the fluctuations are actually different order, or it's just the exponents in the proof are different?
So the fluctuations here will actually be of different order, but the exponents are probably not optimal. The reason for this is that these exponents come from the exponents in the limit shape result for standard FPP, and those fluctuation exponents are not expected to be optimal.
Right. But
So
do you think
these guys aren't either.
I mean, do you think? Okay. Never mind. Let's see the proof.
Okay. All right, we move on to the proof. Okay, so for each positive integer n, we let tau n be the smallest t for which AT is not contained in the D ball of radius n centered at 0. Okay, so it's just, so if this guy here, say, is the D ball in blue, then tau n is just the first time that we're not contained in it. And we note that for any n tilde greater than n, the d distance from the D ball of radius n to the D ball of radius n tilde is equal to n tilde minus n, obviously. And so by the D approximation lemma, tau n tilde minus tau n is going to be approximately equal to n tilde minus n, except in an event of probability decaying faster than any power of n, provided that n tilde is proportional to n. So I say n tilde is between 1 plus epsilon n and 1 over epsilon n. So this means that with high probability, the vertex set of a tau n tilde is going to contain everything which is at d distance slightly less than n tilde minus n of a tau n. All right, so this means that if at time tau n, our cluster a tau n contains most of the things in the D ball of most of the points of the D ball of radius n, then also at time tau n tilde, our cluster is going to contain most vertices of the D ball of radius n tilde. Okay, so by induction, our proof will be complete, provided we can show that with high probability, there's some n0 for which a tau n0 is not too much different from the D ball of radius n0. And in fact, we can just use some basic estimates for exponential random variables, essentially just counting, just fix some path between two vertices and look at how long it takes, and estimate the sum of the exponential random variables along that path. We can find some epsilon greater than 0, which does not depend on n0, such that with high probability, the vertex set of a tau n0 contains each vertex of ZD, which is in the ball of radius epsilon n0 centered at the origin, and such that the time tau n0 is between epsilon n0 and epsilon inverse n0. So things are off by at most a constant factor with high probability when n0 is large. This should actually be an ON0 infinity of n0, because it's a probability. So ON0 of n0 doesn't exactly make sense, but right. So because n0 is fixed, this error epsilon inverse n0 is just dominated by n when n is large. So it doesn't matter where we started at, because when we make n large enough, just the error from the starting position just kind of is dominated by n. And it turns out that this is enough to prove the theorem. So this is how we get the limit shape result for alpha less than 1. All right. So next, I'm going to turn my attention to the result which I called theorem 3 above, because it's easier to prove than theorem 2. Recall that this one says that for any fixed f0, so f0 is the restriction of f to the unit sphere, if we take alpha a little bit bigger than 1, then almost surely a tau infinity contains all but finitely many vertices of ZD. So to prove this, we first are going to quantify how close to 1 alpha needs to be. So if we're given Z and W in the boundary of the Euclidean unit ball, we let gamma delta of ZW be the set of piecewise linear paths from Z to W whose linear segments have length delta and which have endpoints in the Euclidean unit sphere. And we let lambda be the d circumference of the Euclidean unit sphere, which is defined by this formula. So we look at the infimum of the. So essentially what we're doing is if we're given points Z and W in the unit sphere, we want to define the d distance from Z to W considering only paths which are in some sense contained in the Euclidean unit sphere. But of course you can't have a piecewise linear path contained in a sphere. So you have to take piecewise linear paths which are almost contained in the sphere. And you take the infimum of the lengths of all of those. And this gives you the distance within the sphere from Z to W. And then we look at the maximal distance over all points in the sphere of the distance from Z to W. And we take the lim sup as delta goes to 0. So this quantity can be interpreted as the d circumference of the unit sphere. All right. Is this okay for everybody?
These paths go in the ball, right? They're not inside on the sphere.
Well, the endpoints of all of the linear segments will be on the sphere,
Right.
and the linear segments will be short.
The paths are anywhere.
Well, they're going to have to be contained in the Euclidean unit ball by convexity.
In the ball. Okay.
Yes.
And so this looks kind of like a diameter instead of a circumference. Is that not right?
Well, the diameter I would think of as the d distance between any 2 points without any constraints on the paths. But here we're requiring the paths to be in the sphere. So it's really the distance around the sphere, not the distance.
That's what I was asking about. It
between
seems
two
to be
points in the sphere.
but you just told me the paths are in the ball, only the endpoints are in the sphere.
Right.
X delta to 0.
Right, but they're very close. They're piecewise linear paths, and all of the segments have length less than delta, and the endpoints are contained in
The
the
endpoints of each
sphere.
segment is in the sphere?
Yes.
Oh.
So the path is very close to
Okay.
being contained in the
Okay,
sphere, but it's not
sure,
quite.
Sure, no problem.
Right, because it has to be piecewise linear.
As Lionel said, like it's half
Half the circumference.
Yeah, it's half the circumference.
Are
Alright.
we assuming alpha is strictly greater than 1?
Yes.
So there's a typo in this slide title.
Oh, sorry. It's between 1 and 1 plus. Okay, yeah, it can be equal to 1.
It can be.
It can be equal to 1,
Can be,
sorry,
yes.
and this makes sense. It has to be, it's greater than or equal to 1. Okay. The important point about this quantity is that it's positive and it depends only on f0 because the function f is just identically equal to f0 on the Euclidean unit sphere. Okay? So now we're going to prove that. Now we're going to prove theorem 3. Okay. So it's not hard to show that the d distance from the Euclidean ball of radius n to infinity is at least some small constant times alpha minus 1 inverse times n to the 1 minus alpha, where here this small constant does not depend on alpha, but it may depend on bold A and f0. For each positive integer n, we let sigma n be the first time that at is not contained in the Euclidean ball of radius n. This is similar to the times tau n in the previous slides, but we're using Euclidean balls.
What is alpha minus 1 inverse if alpha is equal to 1?
Infinity.
So
in the case when alpha is equal to 1, the d distance from anything to infinity is infinity. Okay. In the case where alpha is equal to 1, it's kind of a trivial statement.
sorry.
Okay. sorry, it's hard to be precise about all of the little details when alpha is exactly equal to 1 on the slides. All right. So by the D approximation lemma, we get that except in an event of probability decaying faster than any power of n, tau infinity minus sigma n is not too much smaller than b times alpha minus 1 inverse times n to the 1 minus alpha. All right, because this is the d distance to infinity, so the time to infinity is approximately the d distance to infinity, which is just this statement. So on the other hand, any 2 points which are in any 2 points of the integer lattice which are in the Euclidean ball of radius n plus 1 minus the Euclidean ball of radius n lie within d distance slightly more than lambda times n to the 1 minus alpha from each other. This follows from the definition of lambda together with the scaling property of the metric d. So if lambda is less than b times alpha minus 1 inverse, then the time it takes our clusters to get around the boundary of the ball of radius n is smaller than the time it takes the clusters to get to infinity. And so this means that with high probability, it's going to absorb every vertex in bn plus 1 minus bn after time sigma n, but before time tau infinity. And this holds except in an event decaying faster than any power of n. So in particular, the probability of the complement of the event is summable. And so we can apply Borel-Cantelli to get that almost surely this is true for all large enough n, which implies that almost surely the cluster A tau infinity contains every vertex, all but finite many vertices of ZD, and that's what we wanted. Okay, so here's a picture. We look at the time that it exits the Euclidean ball of radius n. Time it takes it to get to infinity is b n to the 1 minus alpha over alpha minus 1 at least. And the time it takes it to get around the boundary of the ball is lambda n to the 1 minus alpha. So if this guy is smaller than this guy, then it's going to hit everything, all the vertices of ZD near the boundary of the ball before it gets to infinity. Okay, so that concludes the proof of theorems 1 and 3. And now I'm going to turn my attention to theorem 2, which says that if alpha is bigger than 1, then there exists a norm nu such that if we take f of z equal to nu to the alpha, then almost surely all but finally many vertices of a tau infinity are contained in a cone of opening angle less than pi. Okay, so note that by theorem 3, we can't take an arbitrary choice of norm. There has to be some dependence of this norm on alpha, at least when alpha is close to 1. So in order to define the particular norm that we're going to consider, we need to introduce a couple more quantities which depend on the standard FPP limiting shape of bold A. So first, I let rho bar be the smallest r for which bold A is contained in the Euclidean ball of radius r. And I let bold...
What's known about that?
Absolutely nothing.
Really?
Well, I think there may be some very, very trivial bounds on it. Like it's at most, like as d goes to infinity, it grows at a rate that's at most d over log d or something like that. And I think that's probably the best that's available. So this quantity is not very well understood at all. And likewise, if we let bold x be the set of x in the boundary of bold A, for which absolute value x is equal to rho bar. So bold x is the set of these blue points, which are at maximal Euclidean distance from the origin. Also, there's almost nothing known about this set bold x, but it's a well-defined quantity. It may be the entire boundary of the Euclidean ball if bold A is actually equal to a Euclidean ball, but probably it's not. All right.
Maybe you can say that if we knew more about bold x, then...
Yeah, so if we knew more about bold x, then we would be able to say we'd be able to say more about the norm that we're going to define shortly. But
in particular, maybe we could get it for the Euclidean.
Yeah, that's... Yeah, I guess this is the main obstacle in proving this for the Euclidean norm or the L1 norm or something like that is really that we don't know very much about bold A, and therefore we don't know very much about the metric D, and therefore we don't have very good estimates for the FPP passage times in that case. Okay, so now we're going to fix some x in bold x. And we're going to define 3 planes. First, P sub x is the plane, is the d minus 1 hyperplane, which is perpendicular to x and passes through x. P minus x is the d minus 1 hyperplane, which is perpendicular to x and passes through minus x. And px0 is the plane perpendicular to x passing through the origin. And we note that because px intersects the Euclidean ball of radius rho bar only at x, it also intersects bold A only at x. So here's an illustration in the case when d is equal to 2. So these hyperplanes are just lines. And these 2 on the ends intersect bold A only at a single point. Okay? So now we fix a set Q, which is contained in Px0. And so the Q is a d minus 1 dimensional set. And we're going to require that Q is compact, convex, and symmetric about 0. And that Q contains the intersection of the Euclidean ball of radius rho bar with Px0. Okay? And for a given s greater than 1, we let script q sub s be the s stretching of q, by which we mean the set obtained from the following operation. So say we start with q, which is here depicted as a red line because we're in dimension 2. So q has dimension 1. Then we stretch it by s in the direction which is perpendicular to x. And then we stretch it by 1 in the direction which is parallel to x. And so this gives us a d-dimensional set, which is kind of a cylindrical shape. Okay? Which is kind of tilted in the direction parallel to x. And we call that set script q sub s. So it's easy to see that QS, the script QS is compact, convex, and symmetric about 0. So we can define a norm nu s whose closed unit ball is QS. And this norm nu s is the one that I'm going to prove the statement of the theorem for. So in particular, for each...
Can you go back? So, okay, so for any x, one has such a norm.
Yes.
Okay.
Right. So there's a norm for any choice of x. Okay.
And any s.
And any s.
And any Q.
What?
You can choose
Any compound.
Yeah.
Right. So this is a family of norms.
So
And actually, you can get a family of functions which are not norms also, which are defined in kind of a similar way. But I'm not going to talk about this in the talk. But it is in the paper that you get a slightly wider class of choices of f than what I describe here. Okay. So the kind of more quantitative version of theorem 2 is the following. For each alpha bigger than 1, there exists an s greater than 1, which depends on alpha, such that if we take f of z to be nu s of z to the alpha for this choice of s, then, and we let script k be the union over all r of the intersection of qs with the plane px. So the set k is contained in some Euclidean cone of opening angle less than pi, then it's almost surely the case that either all but finitely many points of a tau infinity are contained in k, or all but finitely many vertices of a tau infinity are contained in minus k. Okay, so this is kind of noteworthy for a couple of reasons. First, we do get an explicit description of the cone, and you can kind of see what it looks like from the norm, from the set script QS. It's just the cone whose boundary lines pass through the boundary of the intersection with QS of the plane P sub x. And furthermore, there's the set a tau infinity has to go off to infinity in one of these two directions. It never can go off to infinity in one of these directions. So the support of the center line of the cone is not the entire set of possible lines. It's only, it has to be in this direction or this direction.
Wait a second. This direction depended on x, right?
Right.
But there could have been an x in one of those other places.
Right, but the norm depends on x. So we're fixing an x, and we define a norm. And if we take this norm, then it has to go in one of these two directions, which depend on x.
Right.
Yes. So Okay. So the reason why we choose this particular norm is that with this particular choice of norm, we can get sharp estimates for the metric D, even without knowing anything at all about the set bold A. Okay, so in particular, we can show that for each q bigger than 1, the D distance from the boundary of script qs to little q times the boundary of script qs is equal to 1 minus q to the 1 minus alpha over alpha minus 1. And furthermore, if we have a point z in the boundary of qs and a point w in q times the boundary of qs, which lie at minimal distance from each other, then it has to be the case that z is in one of those two planes, px or p minus x, and w is just equal to z translated by plus or minus q minus 1x. So here's a picture. If we've got a point, so the inner box is qs, the outer box is qqs. And if we have a point z in the boundary of the inner box and a point w in the boundary of the outer box, then z has to be on one of these two green lines, okay, which are the intersections with the planes px and p minus x. And w has to be the translation of z in the direction parallel to x onto the red line. And so in particular, w has to be on one of the two red lines.
If z and w
Yes, if z and w are at minimal distance from each other. Okay? So the reason why this is important is that if we take this picture and we rescale everything by 1 over q, so that the outer box is mapped to the inner box, then the red lines will be mapped to proper subsets of the green lines. So if you have a point on the boundary of q, script qs, which lies at minimal distance from script qs, and then you rescale by q inverse, you end up with a point on the boundary of script qs, which lies at minimal distance from the boundary of q script qs. So this is crucial for our proof of the theorem, which is going to be by an induction argument. So to set up this induction argument, we define for each positive integer n, we let tau n be the smallest t for which at is not contained in n script qs. So the proof of the first theorem, we used d balls. In the proof of the next theorem, we used Euclidean balls. In the proof of this theorem, we're using nu sub s balls. Okay? And so almost surely there's a unique vertex u sub n of a tau n, which is not in n script qs. And we let gn be the event that un over the nu s norm of un is contained in one of these two planes, px or p minus x. So in other words, a tau n exits the set n script qs at a point which is close to one of these two green lines. Okay? So now we have an n tilde, which is a little bit bigger than n, and the event gn occurs, then accept an event of probability decaying faster than any power of n. And in fact, this is conditional probability given everything up to time tau n. We have that tau n tilde minus tau n is at most n to the 1 minus alpha minus n tilde to the 1 minus alpha over alpha minus 1 plus a small error. This just comes from the de-approximation lemma, because we know the distance from the set n script qs to the set n tilde script qs. Okay? So by a second application of the de-approximation lemma, we get that each point which lies at d distance bigger than this quantity from nqs is not contained in a tau n tilde. But we know from our deterministic estimates for d that anything which is not in one of these two red lines lies at bigger d distance from the set nqs than the stuff that is in the red lines. So that means that nothing which is further than a little error away from these two red lines is going to be contained in a tau n tilde, provided the event gn occurs. So this means that if gn occurs, then with high probability also gn tilde occurs, because we have to hit the boundary of the next ball also at a point which is in one of these two good faces. Okay. So this means that if Gn0 occurs for some large n0, then with high probability also Gn occurs for all n a little bit bigger than n0. So by summing over an appropriate sequence of n's tending to infinity, we get that with high probability if Gn0 occurs, then for each n greater than or equal to 1 plus epsilon n0, we have that the time to infinity minus tau n is at most n to the 1 minus alpha over alpha minus 1. Okay, plus this small error. Now, if we make S big enough and Q0 big enough, depending on alpha, then we have for each Q between Q0 and 2Q0, we have that the d distance of from the part of Qn times the boundary of Qs, which is not contained in one of the two planes, to n times the boundary of Qs is bigger than this plus delta n to the 1 minus alpha for some fixed delta which doesn't depend on n. So by the d estimates, by the d approximation lemma, we find that any point which is not any point in this part of the boundary of Qn script Qs is never hit by a tau infinity. So that means, so here's a picture. Here's Qn script Qs. Here's n script Qs. So if Gn0 occurs for some n0, which is maybe much less than n, then with high probability, nothing in one of these two red lines is ever going to be hit by a tau infinity. This means that if Gn0 occurs for some large n0, then in fact a tau infinity is going to be contained in the union of the sets script k and minus script k, because this holds for every large enough n. All right. So now there's two pieces left. The first one we need is to show that in fact Gn0 occurs with high probability when n0 is large. So this is kind of a similar situation to what we dealt with in the alpha less than 1 proof. But here, in order to deal with this, we need to make S a little bit larger. And in fact, we can arrange that by making S big enough, we can arrange that in fact every point in the boundary of Qs is closer in the metric D to the part of Q star times the boundary of Qs, which is contained in the two planes, than it is to the part which is not contained in the two planes. So then the d approximation lemma implies that Gn0 is going to occur with high probability even if Gn0 over Q star does not occur. So here's the picture. So if S is very big, then everything in the boundary of the inner box is closer to the green part of the outer box than it is to the blue part of the outer box. Okay? So that means that no matter where we hit the inner box, it's going to hold with high probability that we hit the outer box for the first time on one of the green lines, which means that Gn0 occurs. So this shows that almost surely all but finitely many vertices of a tau infinity are contained in the union of script k and minus script k. But there is still one problem left because it's possible that, or I guess we could worry that maybe all but finitely many vertices of a tau infinity are contained in the union of these two sets, but there's infinitely many in each. So it's not actually contained in one of the two sets. So we still have to rule out this possibility that it goes to infinity at the same time in both directions. Okay? So let's let E be the event that this happens. And let's let sigma plus, respectively sigma minus, be the first time that AT intersects script k, respectively AT intersects minus script k, is infinite. Okay? So on the event E, it's going to hold that sigma plus is equal to sigma minus is equal to tau infinity, because it gets to infinity at the same time in both directions. And furthermore, for some large n, it holds that a tau infinity minus a tau n is contained in the union of k and minus k, right? Because all but finitely many vertices are contained in that union. So let's let En be the event that this is the case for a given fixed integer n. So if E occurs with positive probability, then for some deterministic n, the event En occurs with positive probability. But on the other hand, the random variables sigma plus and sigma minus are conditionally independent given f tau n in the event En, because they depend on distinct collections of independent exponential random variables. And so if sigma plus is equal to sigma minus is equal to tau infinity on the event En, then the conditional law of tau infinity given f tau n has to have an atom with positive probability. And it turns out that this cannot possibly be the case for any stopping time tau by kind of a straightforward probabilistic argument, which I'm going to skip for the sake of time. I can explain it afterwards if people are interested. And then I'm just going to end by mentioning some open problems which are related to this model. So first, we show that for each alpha bigger than 1, there's some norm nu for which we have this cone containment result, but it remains an open problem to classify for a given f for a given alpha what choices of f are such that a tau infinity is almost surely contained in a cone of opening angle less than pi. So in particular, if we're given a fixed norm, then does it hold for large enough alpha that we have the cone containment result with that particular choice of norm. And it's possible that you can do a little bit better than our result without knowing anything about without knowing any more information about the set bold A. But I would expect that a full solution of this problem would require some more information about the standard FPP limiting shape bold A. So here's another interesting question. Is it true that for any choice of f, either a tau infinity is almost surely contained in a cone of opening angle less than pi, or almost surely a tau infinity contains all but finitely many vertices of ZD? So we know that both cases are possible for some choices of f, but other choices of f for which neither of these are true. For example, maybe there's some choices of f for which a tau infinity has a spiral shape, or a tau infinity is contained in a cone with positive probability, but not almost surely. So you need to rule out this kind of thing to answer this problem. Then in the case where alpha is equal to 1, do we ever get a deterministic limit shape in this case? And if not, do we ever get a random limit shape? And then also, what happens if we take edge weights which are not positively homogeneous? For example, we could consider periodic edge weights or edge weights which are large in some spiral-shaped region but small in the complement of that region. So we can try to force the limit shape to actually have a spiral shape or something like that. And then there are many more open problems. Total of 15 listed in the paper, which will be posted to the archive soon, hopefully. So here's the list of our references, and
Thanks.
that's it.
Questions, comments?
Yes?
So you mentioned that not much is known about this set bold A,
Right.
but I'm wondering if there are any conjectures about what it should be. Ideas.
So I don't think there's a conjecture about exactly what bold A should be. One significant conjecture is that bold A is strictly convex, meaning that it doesn't have any corners or flat faces. And yeah, this is still not known. If you could prove that, that would be a very significant result about first passage percolation.
Does it make sense to talk about what happens after time tau infinity?
It does. Eventually everything in ZD will be hit, right? Because everything is connected but to the origin by some path with
But not
finite
immediately.
passage time, right? But not immediately. So you could still ask what happens
Eventually,
after time infinity.
there's a quantifier. For any site, it will eventually be hit, but at no time will everything be hit. I guess
I think in the
it can be.
case when alpha is bigger than 1, it can hit everything in finite time.
Right. You cannot give an a priori bound, but it will happen.
Right. I think yeah, I think if alpha is bigger than 1, then almost surely everything is hit in finite time.
You could imagine, at each time greater than tau infinity, there's a ray to infinity in certain directions within the set, but not in other directions. So you have a set of directions which you can reach infinity, and it's kind of expanding, and eventually it becomes all directions.
I think maybe you could have a picture like that. But the one kind of disadvantage of considering what happens after tau infinity is that it has no relation to the Eden model anymore. Right, so if you care about the Eden model, then
Too bad for the input.
yeah. But there's still some interesting questions about what happens after tau infinity.
Yeah, I'm not sure why I say it's not related to the Eden model.
Because the Eden model, you're adding one edge at each step.
Right.
Right. And so
After time omega, you have omega plus 1.
okay, yeah, maybe you could
Finite time for the
Something like
scope.
this.
No, but the point is, everything is filled by omega. There's no left to hold up signs
no.
in the Eden model itself.
In the case where alpha is bigger than 1, our
No,
result
in the
implies.
Eden model itself.
Oh,
Right.
Yeah, but this.
No, but
That's
it's
not the
relating.
topic of this.
The time after tau infinity here is different from time after omega in the Eden model.
Yes.
There's nothing left after omega in the Eden model to do.
yeah,
Everything's been reached.
we're talking about this one.
Right.
Oh yeah, and so just a basic thing about alpha equals 1. So I think my confusion was just, in the case alpha equals 1, tau infinity is infinity, is that right?
Yes.
And a tau infinity is all ZD.
Yes.
Yeah, I mean, it would be interesting to, in the same vein of this continuing beyond infinity. I mean, it would be interesting to just understand some basic things like, can there be a second explosion time, for example? It seems pretty unlikely.
Right.
Meaning what?
What do you think?
An explosion time is a time t such that infinitely many.
Yeah, that's
think that math
for t, but not
in the other
for,
cone. It
not
goes
for
in
every
one
t
cone
minus
first,
epsilon.
and then it'll go in the other.
I think after time tau infinity, every time is an explosion time in that sense, because you're always going to be adding infinitely many vertices in every increment of time after.
Let's define an explosion time as a ray to the a ray from the origin to infinity gets accessible that is not
Well, how
yes,
far?
not in the closure of what was
So
before.
I mean, so if you start out at time tau infinity, you have this cone shape here,
Right.
right? And then so does like a ray like that count? How far away from the cone does it have to be?
It has to be not in the closure of what was accessible at previous times.
Okay, yeah, maybe there's something interesting to be said here. Any other questions?
Thanks, you win again.